files that are fired up. So if you copy and paste this command, as soon as the terminal starts downloading. It's not too big of a file, but because we're all doing it, we should probably do it right away. Alright, so copy and paste it. Alright, sure, that's fine. So do that inside the virtual machine, and I'll start that one. Cool. Alright, so what I've done as well is max out the handouts and green and red sticky notes. So the idea of that is because there's so many of you and I don't want to leave anyone behind. If you're stuck, if you're not sure what's going on, it's like a bug. So like, if you copy paste the command doesn't work, put a red sticky note up, and I'll help you out, or maybe one of the other Aussies or one of the other professors might help you out. Or at the very least, I'll slow down to make sure I'm not leaving you guys behind. And if you have a challenge, I'll ask you guys to do something and you're done, we're going to the next thing. Put a green sticky note up on the laptop where I can see it, and I'll know I can keep going and go to the next thing. Alright, so while you guys are hopefully downloading, I'll introduce myself a bit. I'm Nick Swainston. I'm over from Western Australia. My science background is doing pulsar searches at low frequencies. There's lots of big pipelines for searching, and also pulsar spectra. I even made a little bit of software to help out with that. So what I'm passionate about is solving big data problems, because if you looked at how much data SK is going to push out, you're probably a bit scared like I am. So the one thing I want to do is really help out with data processing, how to manage all this data, how to organize it, how to make nice pipelines to process it all. So if there's any big data problems or software problems, come talk to me. So I like talking about that stuff, maybe I can give you guys some good advice. And yeah. Alright, how are we going? If we're downloaded, also, once we download this one, we'll connect to my car, which is here. Okay, guys. Oh, hold it one thing, sorry. My fault. So unpause this time. So yeah, let's test this out. Green stickies once the file's downloaded and it's unpause it. Alright, so pulsar data types. So we've talked about this a bit already. So pulsar data is typically stored as a three-dimensional array. We've got sort of time and sub-integrations, we've got observing frequency in the channels, and then we also have polarizations. So I'll just mix one. So we have two sort of main types of pulsar data. So we have the raw voltages, which that's just off the telescope, all of the data, massive files, raw and ready to be processed. Then the other type is sort of these folded data, or this fold mode data. Those are sort of the archives, and they're already normally dispersed and folded onto the pulsar period. So they're smaller and they're much easier to analyze. Alright, so there's the two types. So the raw voltage can come to things like PSR fits, PSR data, VDIF, and all you do is you normally use a command called DSPSR, which I'll talk about in a second, turn these into archive files. Alright? So with Meerkat, we have a pulsar backend, which basically means it runs something similar to DSPSR and makes the archives for you. So normally, if you guys are using Meerkat, which I assume most of you will, you don't have to worry about this next command, DSPSR, but you should understand a little bit, because you'll understand what could go wrong with the archives you get. Alright? So DSPSR is already installed, so I'm not going to run these commands, this is just an FYI. So this is what a DSPSR command looks like. So this first part here is the command, and then these are all the different options that you handle. So this is kind of like command lines are really flexible. You can just keep adding all this different stuff, and you can do really complex things exactly what you want. So this is some of the options. This -F is the number of frequency channels. So the telescope might have like 1,024, but you don't want that many, you only want 128. So you can specify how many channels to output. This is where you can add an ephemeris file. So an ephemeris file is something that a scientist or perhaps you have already made that has all the data that the software needs to fold the pulsar accurately. There's things like the dispersion measure, the period. If it's a binary, it might also have like an orbital period, and like a bunch of orbital parameters that are really complicated. But yes, it's everything the file, the command needs. Then we have dash arrow, which outputs mark every 8 seconds, which is what Meerkat does, and then the inputs the raw observation data. Alright? Cool, so does that make sense so far? Cool. Alright, so I might zoom out of it. So one of the reasons I wanted to talk about this at least briefly is because things can sometimes go wrong. Alright, so let's look at what it looks like when things go right. So this is a pulsar, one of our personal favorites. So this is what the pulse profile looks like, right? Like it looks pretty thin, you can maybe see some slight scattering, looks pretty nice. Right, and then here is its phase versus time plot. Once again, it looks nice and thin. So this is a recent observation. So this is with an ephemeris that we've got pretty good, it's pretty accurate, so we get a nice, strong, sharp profile with a nice resolution. But if I go back in time, back to 2019, before we really nailed down this pulsar's period and all that kind of stuff, if I do the same thing, it looks a bit wide, right? So this isn't actually because the pulsar is wide. The problem is that because our time wasn't accurate, in those 8-second archives, it doesn't perfectly line up. If you kind of think about like each sub-integration, it's not perfectly vertical, right? If you're going to do an angle, and that causes the pulse to be wider and for your observation to be less accurate, less sensitive. Does that kind of make sense? So it's more just an FYI. If you ever see something that looks too wide, it might be because from an early observation where the time wasn't perfect, and you kind of can't fix that because they're already in 8-second chunks, so you can't undo the 8 seconds. They've already been squashed, right? Does that kind of make sense? Yeah. Alright. Oh, and if you ever suspect this and you want to check, there's this command here, that -E in the archive file. What this will do is it will output the ephemeris file so you can compare it to your current one. So I'll show you what that looks like. So I've already got, the archive file, so with that -E, I copy and paste this command with Control Shift C, Control Shift V. Then you can see it outputs the archive, the ephemeris, and all the data. So the frequency derivative, period, DM, also tons of terms. This is really what time binary is, what the binary period is, a bunch of the binary parameters, all kinds of stuff. Cool. Alright. So now that we have some archives, let's do even more analysis. So the main program that we use for like known pulsars, for analyzing them, is called PSarchive, or PSarchive. So I've got some links here. The software is documented online. The documentation isn't perfect, but it's alright. It tells you most things. So you can go here, you can use, and have all different commands. Let's go back. And there's also 2 papers which describe it. And this is also what you should reference if you use PSarchive. Alright, so there is a full list of the commands online. There is a lot, but I'm today just going to talk about the most common ones and also kind of my personal favorites. Alright, so this is the list. Oh, this is my list. Alright, so there's a few. There's PSAR which queries the attributes, PSAR which combines data. So like I was saying before, Meerkat outputs the files in 8-second chunks, someone uses to add them all together. So there's some plotting things. There's an RM fit stuff. I'm not going to go through RM fitting today, but you should know about it. You can look at the documentation and also a bunch of things. Alright, so now that we've talked about it, let's do some interactive things. So we have 2 archives. Let's have a look at them. Let's see what the heck they're about and some of their data. So what we can do, let's start copying and pasting commands, right? So let's copy and paste this Zap command. because there's two main commands that you can query the data. So there's VAP and there's PSR stat. They're slightly different. VAP is kind of makes nice tables. PSR stat doesn't make nice tables, but it gives you more stuff. So it depends what you want to do, which one you want to do. Let's compare them. So I'll copy paste this. Yeah, so what you can see in the output, so what I've done is I've gone back. The dash C option says this is the stuff I want to query. This is the stuff I want to know about. So I do n-channel, so the number of frequency channels, and sub, the number of time sub-integrations, and length, the length of the observation in seconds. Alright, now just give it a file. Alright, then it makes a nice little table for us. So, okay, cool, it's got 1,024 channels, 31 sub-integrations, and it goes for 248 seconds. So it's a pretty short observation. That's why I picked this nice one, small file. Cool, hopefully that command works for you guys. So let's compare it to PSR stat command. You notice that they're called something slightly different. This one's called n sub-int in PSR stat. But it should output very similar things in just a slightly different format, you can see here. Right? I'll just give you guys a second to use those commands and make sure it still works. Red sticky notes if it's not working. I'll assume you guys are all good. Anything so far? Alright. So just to reiterate what these things are. So once again, n-channel is number of frequency channels. That probably makes pretty easy sense. Number of frequency things. The number of sub-ins. So you can have, so actually let's start with length. So length is the number of seconds. I think that's pretty easy to comprehend, but how long the observation is in seconds. But then what we do is we divide it up into time sub-integrations, right? So we can do, maybe make one for every single pulse, every single period. But obviously, sometimes that doesn't really make sense unless the pulsar is really bright. So often we make it into even smaller sub-integrations. So for example, this one is in 31 time sub-integrations. So basically each sub-int is 248 divided by 31 seconds long, right? That kind of makes sense? The size of that normally depends on how bright the pulsar is. So basically you want each of these sub-integrations to be bright enough that you can see the pulse. And also often enough pulses that it averages out. You don't get sort of the jitter or the weakness in the pulse, kind of averages out to what you expect. Make sense?
So why is the amount of sub-intervals then more accurate or not necessarily?
Not quite right. It's alright, so normally we use this for pulsar time, right? So each of these times of integrations will be its own time of arrival. So if I actually go down, so like the TOA is something like this, right? Now you want a nice bright pulse, so you're very confident when that pulsar's time of arrival is. Is it right? If you use a very large number of sub-integrations, your pulsar will be bright. Pulsar is not as bright, it's not as accurate for the time of arrival, and you're going to not be able to time the pulsar very well. But then in the opposite way, if you do too few, you're not going to have as many points to measure the pulsar. It's a real compromise, and there's no wrong answer. It depends on the pulsar and also like how wide it is at that day. Yep.
So when you use these sub-integrations, you're basically folding the switch and output data for each other, then you can't hold it to the
Yeah, so yeah, we go to the next one exactly how to do this. But yes, basically, yeah. Yeah, so this first lesson is what I'm going to do. I'm just going to be how to get the data ready, and then I'll be handing back to the current garage. Cool. I'm going to put on 5 minutes. Alright. So I just showed you a few of the bits of metadata that you can look at. And often you only want to look at 1 or 2. But hey, let's say you want to know everything that's in there. Time to do something that's scary. Right, so let's copy and paste this last command. So you see there's no -c option. So this is going to get everything. So let's have a look at all the data that there is. Just a little bit. My fingers getting sore. I'm scrolling up. There's so much. Right? There's so much data. So it's often if you just get a file and you're like, I actually don't really understand what this is, it's often good just to run this handle through. So let's see what we can see. So let's see what the telescope is. It's Nick, fantastic. What the source is, this is the pulsar, this is where it was pointing, center frequency, so you can work out which band it is, maybe if you don't know which band it's using. So this is L band, right? Yeah. Dispersion measure, rotation measure, tons of good stuff in there, right? Cool. So let's clear that. Alright, so now that we understand the data bit, let's make some plots. So the command we use to make plots is called PSR plot. It can make a bunch of different plots. If you want to list all the kinds of plots it can make, you do PSR plot -capital P, and it outputs a list. There's a lot. You probably don't. You probably won't do all these, but I'm going to show you my favorite ones, the most useful ones. All right. This is just an FYI. All right. Now I want you guys to do these along with me. Let's make these plots together. All right. So this is the pulse profile. This is probably the most common one. So I'm going to explain this really quickly. So PSR plot's the command. I now use lowercase p, and then I tell it the type of plot I want to make. So this plot, see this was shown in the type of plot, so here you go, single plot, 4 plots. So that's what I want to do. I want to make it, or I want to call this a pulse profile. Alright? So then I've got a bunch, oh wait, oh I missed a bit. Before I talk about plots, let's talk about PSR SH. So, let me just do water. Alright, before we make these plots, we can manipulate the archives in a certain way before we plot. So we do this with this command called PSR-SH. Basically, it's a way we can do commands before we make things. So this -J option, you'll see it a lot in PSR archive. Basically, it says, what commands do you want me to do before, like in this case, the plot. So the most common use is to change the archives, like number of frequency channels, number of sub-integrations, and stuff like that. So it's what we call scrunching. So if I say frequency scrunch, what I mean is I'm going to change the number of frequency channels to 1. So I'm scrunching it like this. Right? And same thing with time. If I say time scrunch, scrunching in time, single sub-integration, right? Alright, so that's what each of these mean. So T, if you give it J and then T, it will time scrunch, F will frequency scrunch, lowercase p will polarization scrunch, so instead of having 4 space parameters, you just have 1. D will de-disperse, so if it's not already de-dispersed, it will. This is often redundant, but it's not bad, I just put it in anyway. And S transforms to the scope parameters. So let's have an example. So for example, if I use J, so -J, T, F, D, E, so that is time scrunch, frequency scrunch, de-disperse, and polarization scrunch. Right, does that make sense? Alright, so what you want to do, how many many of these you want to do will depend on, well in this case, what type of plot you want. Alright, so for example, the pulse profile. So all we want is a single pulse profile for the entire observation, right? So we very much want to scrunch everything. So we want a frequency scrunch, time scrunch, dispersive, and polarization scrunch. Right, so that's why we use this little data. So far so good? Any questions about that before I go on? Yeah, question?
So if we're saying we scrunch the frequency,
Yeah.
tell us which frequency we're just looking at, and for instance, the outcomes as well. Does it tell us to what value of time scrunch, to what value of frequency scrunch or not?
So when we're scrunching these things, we don't care about an individual frequency or individual time value. You kind of just want the total, kind of the average, right? So instead of, we want to be, when we're frequency scrunching, we don't want to look at individual frequency channels. We just want to smush them together and look at the total. Make sense? Yeah. Alright, so that's what we're doing. Any questions?
Sorry, in the previous mode of the sub in equal to 1, that becomes 1.
Yeah, so if I do capital T, yes, that is the time scrunching. So it makes the n sub, number of times sub integrations 1. Yeah, cool. Alright. So then the next part of the command, dash D. So this is saying what to add. You don't actually have to include this. If you don't include this, it will, by default, it will just show you it. But I like to always save images. So that's what this does. So this first part is what I want to save it as. So I'm going to give it a fairly good name. I'm going to give it a pulsar name, and I'm going to say profile, frequency, time, slash. Well, PNG. Then I have to do this slash PNG. This basically says I want you to make it a PNG. Because fun fact with like Linux, you can put a .png at the end, but it can be like JPEG. So this is just saying, yes, go to the file name, it should be PNG, and it should actually be PNG, that makes sense. Yeah. Alright, and then at the very end, I just put the archive on that. Alright? So, let's give it a go, right? Let's copy and paste this. Control Shift V. Might take a couple seconds. We've got to do all this scrunching, chase a little bit of time. Cool. So probably the easiest way to look at it is let's go back to the file manager. And let's go to Pulsar data lesson. And look, there's a new PNG. Double click. Success. Cool. One last little thing. Actually, no, look at that. Is that? Yeah. Alright. And I think if we can get that, boom, one keep going, and afterwards we'll keep going. Making some plots. My favorite thing. Alright, so what I was doing before is just running this command here. So one thing I wanted to show you, so most of the time it's good, like I said, just to dump an image file, because then you have it forever, and you can use it in validation or show your supervisor, whatever. But sometimes you don't even want a file. So what you can do is I'm going to remove, you see this dash D command? I'm going to remove all of that. And then what will happen is it will say, okay, you haven't given me a dash capital D option. Where do you want me to put this like output, right? And by default it's X window, which basically means an interactive window that will just pop up. And, oh look, there's an interactive window. It's got it cut for me. Now we just wait a second for it to actually do the scrunching. And boom. Now we just have to, so this hasn't been saved. We can just interact with it and just have a quick look. Maybe if only something quick, this makes more sense. Cool. Alright, so let's power through the rest of these plots. So remember to copy and paste along with me, and feel free to ask questions if you don't understand it. Why is that slash? Alright, so now let's make a polarization Stokes profile. So very similar, but it has the sort of the Stokes line and line and stuff. So you can see this is the linear polarization and this is the circular polarization equilibrium. So the way we do that is we do this option here. And one thing you might notice in this command is we didn't put the lowercase p. Because we don't want the polarization to one, we want all the Stokes parameters, right? So Control C, Control Shift V. I actually don't know why there's a slash J. That might be hard on my part. Alright, that's a load. Success. Alright, hope that helped you guys. If it didn't, remember to stick up some red sticky notes if you're struggling.
Just I don't think we've spoken much about polarization.
Oh. I don't know if I should talk about polarization. I'll bring this things up. Do any of the scientists want to briefly talk about polarization?
So we 2 seconds, and then I won't really say too much. I just want to you mentioned the word Stokes, so I don't know if you guys are familiar with Stokes parameters. I think the only thing I'll point out is that something like the secret has got a linear feed, so it means more linear polarization, so you get combinations of horizontal and vertical. And you can rewrite those, we can make because the equation later, you can rewrite those in the so-called Stokes parameters that describe the combinations of the electric fields and their x and y components. And principally, when you're doing pulsar timing, and I think for most of the rest of the workshop, you'll only ever care about what we call total intensity. So this is the white plot here. So that's Stokes I, if you will. So that's total intensity, and that's the exact same as if you've done the scrunch P, as if you've taken the polarizations and average. But if you wondered from that intensity what fraction is maybe linear polarized or circular, this red one here is the linear component. So in Stokes parameters, that means you've taken Q and U, you've squared them, you've added them, and you've taken square root of it. You don't know about that, it doesn't matter right now. What we can see here is that this pulse profile, this red is the linear polarization component, and so we learn that the pulsar has significant linear polarization. And without going into any details, this is somehow already interesting because we know that the pulsar has a magnetic field, right? So we know that means there's some polarization plane that we must somehow describe that's related to these open magnetic field lines along which we're streaming particles. And so when people do research to understand what exactly this emission mechanism is that produces pulsar pulses, then we do a lot of study to look at, for example, the linear and circular polarization. But for timing, oftentimes what you really just want is high signal to noise, and so we just go with the Stokes line. I don't know if anybody else wants to say anything about polarization.
Is the circular domain?
Yeah, so what does it mean?
Negative flux or negative flux?
It's just a sign. So you can have right hand or left hand circular, so it's just a sign. No, it's not.
Perhaps one other fun fact about polarization is it's one of the ways we use to search for pulsars and imaging. Because many astrophysical objects aren't linearly or circularly polarized. So if you see some imaging that is, you go, oh, maybe that's a pulsar. That's a very, very quick explanation. There's a lot more to it than that. Alright, on to the next one. Phase versus frequency. Alright, so this one, we didn't put dash capital F. We have the frequency scrunch, because we want to look at the frequency, right? So let's go up on the base. One's done. Have a look. So I think we talked about this a bit before. Let's have a quick look at this. Yeah. So on the y-axis we have frequency, on the x-axis we have pulse phase. So you can see it's not quite consistent throughout the frequency range. This is very likely scintillation, which is much wider than frequency. You can also see other sort of like horizontal lines where there's not even noise. That's the part of the spectrum that we've already zapped. So that means, so by zap I mean remove that frequency because it was RFI'd it and it was making our oscillation worse. Cool. Alright. Next one. Alright. Pop phase versus time. Alright, so in case you guys also haven't already noticed that this is deadening, so it's a bit different. The like taskbar is at the top, so that's why I'm going back into the hot zero. Alright, so this one I'm at time, so I didn't put the capital T. Let's have a look at this one. Alright, so this is a nice plot. The y-axis is time. So you can see it's consistent throughout time, so it's not like a number or anything like that. It seems to be continuously emitted. One nice little thing to check in these as well is to make sure that it's vertical. What I mean by that is it doesn't sort of go off to the left or right. If it went off to the left or right, that basically means we haven't actively measured the period. So we're not actively stacking them up in time. It's kind of going over a slight error, so it's moving to the left or right. That's one way to check that. That's why this plot can be useful. Cool. Alright, clean band pass. So for this one, we've only scrunched time because we care about things. Actually, I don't think it matters. I think we can scrunch more things, so that's all we need to do.
So these plots should remind you that when Matthew and I think other people also put up to show where the GPS signals and the RFI is. So from your Pulsar data, you can just keep the frequency and the average and the others with that.
Yeah. So what this is, this archive I've given you, we've already done some RFI zapping, so some cleaning of some of the radio frequency interference. So that's why you see these like massive dips. This dip is saying, alright, I've set this to 0 to not affect the observation. But you can see there's still some spikes. So we perhaps didn't do this perfectly. We could probably do some more archive zapping, but you know, we can see the pulsar pretty brightly, so it's probably fine. Depends how accurate you want to be. Like I think some of the relativistic binary guys, I've seen some of their data, and they go really fine. They've moved everything. It looks beautiful, but I'm not going to spend that much time making that. Cool. And we're actually going to do that later, so that would be fun. Oh, actually, here we go. Alright, sweet. Alright, so now I'm going to give you a data file that hasn't been cleaned, and we're going to give it a red hot go. So like I was saying before, you can see what RFI has been cleaned. So I want you guys to run this command, and we're going to have a look at what some unclean data looks like. Why isn't this work? Oh, sorry, my command's wrong. Actually, I'm going to show you guys how to do this. Alright, so I've put a bad command, but instead of thinking of that as a bad thing, let's think of it as an opportunity to just show you guys something. So, let's have a look at this error. So it says, file name not found. So let's do a bit of Unix to work out what's going on. So ls, let's have a look. Does this file exist? No, well, like it almost does, but there's one thing wrong. That's capital T. Alright, so let's just add that dot capital T, and we can run that. Cool. Just FYI, I think I told you this a bit later, but I added that, so that capital T basically means time scrunch. That's what the command is. That's one of the ways you can make your file names a bit clearer what it is. Our time scrunch is because we don't really care about time, it makes this file smaller. Alright, so let's look at that plot. So it should be this one. Gross. Right, so let's have a look. So they've got all these sort of horizontal bits of scruff. That is different sort of RFI than the off the top of my head what this is. Maybe it's, I don't know, is it, I've memorized the frequencies of satellites and all that kind of thing. And the annoying thing is that we can't really see the profile anymore. That's how bad the RFI is. So this is a good one to say, all right, let's fix this up. Let's bring this RFI. All right, so we're going to do that. There's a few different ways to do RFI decision, and I'm going to show you a few of them. So the first one is PAS. PAS is Gibbs archive, and it can do some automated basic stuff for you, and also some actually some manual stuff. Well, let's try this command first. So let's have a look what it says. So -R is basically remove the median. So it's one RFI technique. Actually, let's see if it's explained it better. So I think that really makes sense just by itself. That's one. Dash R. Zap channel using median smooth difference. So that's one method. There's 101 different ways to do RFI, but let's try this one first, right? So let's look at the rest of the command. Then I'm using this -lowercase e option. What that means is what is the name of the extension? So what I'm basically saying is I want you to change the last bit, the dot something, to PAS median. The reason I'm doing that is two things. One, to make a new file. I don't want the same file, I want to be able to compare. And two, so I know what I've done. So I call it PAS median because that's the type of RFI technique I'm doing. So it's clear what file is what, right? And then that's just a file. Now I've done the, guess what? This command is wrong. Put a -T. Alright, that went pretty quick. So you can see if I go ls, we've got a new file. Right? So now let's make this a plot. With this command, so we're doing pretty much the same command as before. Adding .t again. We'll go like this. Alright, do this one. I'll give you guys a second to catch up to everything now. So one other little tip as well. If you're like me, you're starting to get annoyed about having to open up this and go, where the heck is my file? I'll show you how to do it in the command line. Alright? So, one little helpful command. So what you can do is one of my little commands. Instead of just doing ls, you can go -lrt. -l is more information, the -r is reversed, and the -t is time. So it shows you the most recent files as well. So you can see the most recent file is this PNG I just made. So what I can do is I can just do the command open, which opens the file. And Control Shift V. So now I've just opened it. And that's sometimes a bit easier than having to go to the file manager and clicking it. Does that make sense? Yeah. Cool. Alright, so now I have it open. Let's talk about that. Alright, so if we look at it, it's kind of hard to see. Hopefully you guys can see the video on your screen. But actually we didn't know what's up. That's not right. Alright, well basically what I want to say is that it zaps some things. You can see there's no noise in parts of it. But the most annoying thing is there's still some bloody RFI. So it hasn't been perfect. Lots of these zapping techniques aren't. So let's work out how to do some manual zapping. So let's do this by hand, because humans are pretty good. We can remove lots of RFI if we want. But at least you can actually start to see the profile. You can start to see the pulsar a little bit. It's faint, but it's there. Alright, so now for the next command. Oh, also, sorry, I did skip one thing. So, what I just did was in 2 steps. So I made an archive and I plotted it. But, you can make it a bit more automated because PS archive is pretty smart. You can add this zap median command, which basically what it says, in the same way we were doing like a scrunch command first, you can also do a scrunch command and then a zap command, and just make an archive. This is kind of instead of doing 2 steps, just do 1. Might be good, might be bad, up to you guys, personal preference, depends on the situation. But it'll not be the exact same file. Right, so now use PAS-E, with a line in interactive. So if you just do PAS-E by itself, it will output some help. This help is very useful because it's a bit confusing without it. But I'll go through you guys. So the important parts are reset zoom. We have different modes. I've actually time scrunched this, so the time one's going to look silly, so don't worry about that. We're going to look at the phase versus frequency stuff, right? That's the one we're zapping. And the way you zap it, you can right click for single channels. But there's a lot of channels, so what we're actually going to do is left click and right. So I'll show you how that works. What we're going to do, go back to my command line. So what's the file? So PAS on. Then I'm just going to hand it. I'm going to do the one I've already zapped. You can also do the first one if you want. This is what I'm going to do. Alright, so this first thing this is because by default it does the time version. But because of the time scrunch, it doesn't make sense. It's just one thing. So press F, and you go into this one. Alright? Actually, you know what might be easier? I'm going to close this for a second. I'm just going to change this slightly so we make it easier for you guys to read. Alright. Alright, so just to make it easier, I've got the help on the left and the plot on the right. It might be easier for you guys to see what's going on. So first thing, I want to go to phase versus frequency. So I'm just going to click here, press F, and now that's what it looked like before, right? So you can see the RFI here. So let's zoom in a bit. So I'm left clicking once, see that's where the line is, then I'm left clicking again. I've zoomed in. So now what I'm going to do on is that there's garbage looking stuff here and here. So what I'm going to do is I'm going to do, where is it? Zap multiple. So I'm going to left click and then I'm going to right click. So I'm going to left click at the top, then I'm going to right click at the bottom. Boom, it's gone. That easy, magic. Alright? And then I'm going to do it again. Left click at the top, right click at the bottom. Oh, no, there's more. Oh, it's everywhere. It's multiplying. No, that's not good. Hopefully that's fine. Okay, so now I'm going to do, so now I'm going to save it, right? I'm going to click S, and I'm going to click Q, click. Alright, so now I can see back at the command line. So now you should see if I go to SLRT, there's a new .PASI file. So by default, it just happens to file with .PASI. That's a new archive. Oh, it looks better. I've done way too much, but it looks better. Alright, so now for a challenge. Alright, so now if I go back for a second. Alright, I've got a little challenge here, that's what this looks like. So if you use this command here, what it's going to do is it's going to output the same noise. So I'm going to control C, control V, and I'm going to give it that new PASI file. Alright, so the super noise is 183. But I reckon you guys can do better than that. Alright, so I'm going to do, I don't know, let's say 10 minutes. Oh, maybe less than that, really like. No, wait, 10 minutes, play with PASI. Maybe don't start with that PASI medium file, maybe start with the original archive. See how good you can get archives at them. And see how high the synchronization you get. High synchronized wins, right? Very competitive, let's go. if you guys started with that dot pads medium file, you probably couldn't get the synchronized as high as I did. The reason for that is that algorithm might have been too harsh in places. It might have removed too much data. So there's less like frequency bandwidth for it to add. There's not enough like pulse, and there's not enough signal, right? So like RFI mitigation is a balancing act, right? You want to remove as much RFI as you can, but you don't want to remove too much data because that will reduce signal noise, right? Alright, that being said, we'll call that there. We can definitely still play with this, I don't know, in the tea breaks if you want, but I can have you guys out a little more. So we'll call it there. So let's see how you guys rank. Hopefully you guys got numbers. Let's see how we go. Alright, anyone? Hands up if you're over 150. That's pretty good, that's a nice number. Alright, anyone over 200? That's still going. Over 250? Alright, let's see if you can beat me. Over 280. Oh, we are! Oh, nice. Alright, couldn't fit the other. So, I'll go back. So what I actually did is, so if I do this piece of automatic, and I'm going to add dash D, so that we have to do the X window, that is an X window. And now what I can also do, if I go back to the okay, that's fine. And if I now go back to my passive see how we break out at the same time. So, if I start moving there, there's updates. So it's like 9 seconds now. 143. So, I think that's quite enough. That might help you give you a rough idea. Oh, am I starting to go too far? Am I adding too much data? Is my system over there? So yeah, that's something I'd like to do. One other thing I wanted to mention, so I was kind of talking to some of the students about this, is very likely you won't be doing 1 or 2 observations, you'll be doing like hundreds and thousands. So it doesn't really make sense to manually go through like it's a good learning experience, but it doesn't make sense for a large number of observations. Perhaps you're going to do this on like a couple that are really important and really interesting. But most of the time, you just want to like have a command that fixes it for you, and most of the time you don't worry about that, right? And that's why we have different stuff like this. So then the radar here made Mega, which is part of this other program called Pulsar, and it does some really nice RFI stuff. So she doesn't that's what I does. Hopefully it's going to make sense by me introducing new things. So if you have a template of your course profile, what it should look like, you can run that over an observation. And then it doesn't really fit that profile. If it's too noisy in the off pulse, so the period. So the on pulse is where it's also time. The off pulse is everything else, that's the noise, right? So if the off pulse doesn't look like it should, in the pulse profile, then you can zap it. And that does a pretty good job, and that's actually what I did. So I ran Media on the archive, it did a pretty good job, and that's what we were running that first one. This is an FYI. Really nice tools exist, and this was what Nick had used most of the time. This program. But we haven't installed it on VM, so we're not looking at that's just a quick FYI. I'll still go with it. Alright, so that's RFI. It's a bunch of fun. Now I just want to talk to you about one other command. It's called PDMP. The goal of what PDMP does is it tries to find option period and dispersion. So this is only useful if your memory isn't very accurate. So for example, maybe you've got a new pulsar and you're trying to get the timing as accurate as possible. So what I was mentioning before is like if you have these phase, this is the output of the command. It has these phase and time clock and phase frequency clock before. If these aren't like vertical, that means something's wrong. So if it isn't vertical in phase less time, it means the period is an accent, so no matter the slope. So it's not like 1 second, wait 0.9 seconds, so every time you stack the pulse it's off like it's not perfect. Does that make sense? Maybe? And if it doesn't make sense. No one's going to do it? Okay. So the experiment. Alright, so the other one is the phase versus frequency plot. If you see a sweep in the phase versus frequency plot, that means that the end dispersion measure is inaccurate. Right? So if you look at it perfect, it won't line up well, and there'll be some residual dispersion, some residual sweep in frequency. So if you ever see those in the plots, run PDME, and that should give you a more accurate value of the period at the end. And then you can put that back in your furnace, and you should then get more accurate, more sensitive to its data. So your post profile, instead of being like wide, so this is accurate, this is stacking up. Your post profile isn't going to be nice and sharp, is it? It's going to be wide, and that's going to be less sensitive, lower central elevation. Does that make sense? Alright, so this is, you can run the command here, but it will take a while. So you just do that, but just be warned that it will take. It takes a while. It's sort of like, we'll try this different periods in the end. But here is the divide that you did earlier. So it gives you lots of nice things, like what it links to the periods, and what it links to the ends. So that's really nice. You also outputs in the file. One little note, it gives you both barycentric and the topsy. So as was mentioned earlier, barycentric is the center of mass of the solar system, so pretty close to the sun. That's the time that you want to put into your focus and you want to give to the mass. So the Pulsar software, pretty much all of them, give them barycentric periods of frequency. And then we'll convert that to toxic. Because, as the Earth orbits the sun, depending on that place they orbit, there are different distances, different relative velocities, different stuff has to go through. So it has to go. Right? So just a quick note, if you're doing this, grab the barycentric. That's the one you care about. Kind of don't even bother with the toxic. That make sense? 2. Alright, second last thing, destination. So we kind of talked about this indirectly. We were talking about scrunching and number of channels and number of subtypes, right? So destination is what you do. One main benefit of destination is it makes the file a lot smaller. So for example, if I scrunch the frequency, instead of having all these arrays, all these floats of different frequency values, the structure the file a lot smaller. And because Pulsar data can be pretty big, that's often a good enough reason in itself. The other good reason is this is a step before using before doing TOS stuff, which we talked about next episode. So for example, if you've worked out how many frequency channels you want, you might not want 1024. If you do 1024, it's not going to be enough frequency bandwidth to apply pulse, so let's put that down to 16. These are commands that will do that for you. This is what command looks like. So it's pan, that's the destination thing. You set n chan, which is the number of frequency channels. Set n sub, number of time sub-inversions. And optional, that's if you want to scrunch polarization. For timing, pretty much what you do. And then the dash D output. So, this is my personal preference of how to label things. But it doesn't mean it's the best way. But I always think it should be clear what your files are and what you've done to them. So this dash D, if you remember, will be the last little bit. This is how I reckon you should do it. So you should do n-chan and chip. So you say, okay, this number is the channels. Maybe 1 if your polarization structure, or 4 if you haven't, then P. And so, and then T. So number of right? So let's give an example. So for example, I want to do 16 channels. So I go 16 chip, 8 subbands, 82, something like that. That kind of makes sense, so it's clear what this file is, what you've done. You don't have to use like back or anything to print the metadata. You just like, okay, I've got this stuff in the file name, I know exactly what I've done. Make sense? Alright. Cool. Alright, last little odds and ends. Because I'm very passionate about data, a few general organization tips. Because you might be dealing with a lot of data and being clear and organizing things well, will hopefully save you time for everything to get in. So first one, use good names for your file. If you've already RFA in the file, maybe add like a stat or something, make it clear what you've done. If you're trying a few different things, so when you're doing the Tasmanian, at that end, if you're trying media, back the file name, so you know what all your files are. Make it super clear. We have the Pulsar name, we have the UTC's video observation. Make a script to automate your work. So when you're first trying stuff out, often you just hang around and alright, go to this, go to that. Once you've worked it out, what you should do is make a script. So what I mean by that is you can make a thing called a bash script as well. Basically, it's a list of commands to execute one at a time. So for example, for like today, you might go, alright, first command has the dash R option in my archive. Then I want to do all the different hot commands, and then I want to do a decimate command like that. Instead of doing this manually, you see now. You might forget to do one as well. Put it in the script, and makes your life much easier. Your time is much more valuable than the computer's time, so try to automate as much as humanly possible. Yeah, I can talk to you guys more about that, but just I push this could be a whole separate lesson to teach you how to do that, but just applies. Another thing is to use the Kanban board, and if you don't do that, what's basically like a to-do list. If you have like hundreds of observations, you might think of which type of business you can process, or what stage the possibly is, maybe one area that fits it. Maybe one's really interesting. Kanban boards are an easy way to track that. One app I recommend to do this is Trello. Even got a link here to a lesson of how you can organize data. Like a sweet action example. So mine looks like this. So alright, this is my ECS data processing pipeline template. So I can describe what the observation is, when it starts and ends, and I can have checklists. So yep, I've downloaded the data, I've been formed it, I've run the presto. This is very common to my work. It was my boss say, oh, I've decimated RFI many ways. That might just help you keep the team more organized. Things will change. I think about that. Alright, last one is take notes of the commands you use. This is normally good just because there's lots of commands out there. You might just forget what you did. Either to understand why the file is the way it is, or if you're trying to do something similar. So there's this nice thing in Linux where you can string commands together. So what I mean. So if I go to history is a command, so I press enter. These are all the different commands that I've done today. So you see it lists the number, it lists the time, it lists that date. Right? So if I scroll up, I can go, okay, this is where I started, this is where I am. So 174 to 229. So the last 50 commands is what I did today. So I want to record that, I want to go to a text file, just in case I did. So what you can do is, see this is the variable line, so it's called a pipe in Unix. And you can, what that basically means is the character history, I'm going to put into another command. This is why command lines are really good because you can extract them together. It's a bit confusing, but hopefully this kind of makes sense. Then I can do another command called tail. And I go tail, take 50. So what this basically says is grab history, put it into this command, and give me just the last 50. Enter. So if I now scroll up, see it stops. And I'll do 1. now I've got this all the commands I've done. Cool. Alright, any last questions about this stuff? You guys know Python and stuff I'm talking about. I have very strong opinions about that stuff. Yeah, I'm done. So now your data's cleaned, you checked it, you formatted it, now it's ready to make some TOAs. So that's hands off. Alignment.